Okay, let's get started with tutorial 2, chapter 2, walking through Spartan. And just a reminder where that's located within the program. If you go to the activities menu and then the tutorials entry, this is just a little HTML panel. Okay, let me zoom in on this so you can see it a little bit better. And the second entry is walking through Spartan. Okay. I won't read all of this to you, but it probably does a better job summarizing what we're going to do than I can. We'll look at opening molecules, we'll view different model styles, manipulate the molecules on screen, measure distances, angles, and dihedral angles. We'll display energies and dipole moments and atomic charges, also IR and NMR and UV vis spectra. I think we do graphical surfaces, and then I think we also display multiple molecules. So there's a lot going on in this tutorial. It will take a while. We'll look at a number of different molecules. The first thing you need to be able to do is open a file which is called Walking Through Spartan. And so in order to do that, we need to talk about where that's located. Let me just go down to the bottom of page, this first page, and I'm going to sort of make this window a little bit larger so I can zoom, so this will maybe be a little bit better for you guys to see. Okay, so for Windows, there's a tutorials directory. Okay, it's found in the program files, wave function folder, Spartan 24, and then whichever version. The latest is 130. Okay, for Macintosh, it's located, it's on the disk image. Okay, so the same piece that was downloaded in order to install the program. So just copy it over from there. For Linux, it's actually located in the installation directory. And it's just a folder called tutorials. Copy that to the home directory or the desktop or some user writable location. The same is true for all platforms. It gets installed in a location, you need to be able to open it. I'll give you just one additional location where you can access in case for some reason you're unable to find things. And that is actually if we visit our website, which is wavefund.com. If you go to wavefund.com and go to the support entry, and it's the third item down is Spartan documentation. You'll find under Spartan documentation, the third item down as well is the tutorials file. This is a zip directory, and then also immediately under that is this file, the Walking Through Spartan file that I have just opened and that we'd like you to open. And this file contains about 16 molecules that run a sort of they're all organic. They said not a lot of variability, but just to highlight different menus, menu items, and then also different functions within the graphical interface. So again, let me just pull the Walking Through Spartan tutorial up again, just to show you again where it is, and then I'll push it off screen. There's no reason to refer to it from this point forward. It's useful for you if you want to follow along, but I'll be demonstrating essentially everything in the tutorial. Okay, so the Walking Through Spartan tutorial file contains 16 molecules. You can see that if you look in the lower right interface. You see one document is open and it says 16 molecules are in that document. I guess the other comment to make is that the molecule on screen is ethane. You see its name in the lower right. Spartan is not a naming program. This just means it recognizes the molecule in a database. Okay, so ethane is on screen, and it should be roughly centered on screen. And in this portion, what we'll do is we'll just get used to using the mouse. So I'm going to describe using a 3-button mouse, right mouse, left mouse, and then a center mouse wheel. Touch operations are described in the PDF file, and of course I don't expect anyone to remember all of the different variations that are mentioned. I'll just point to a location where you can refer to help with mouse and keyboard commands if you need those. And that's the help menu, Spartan 24 help. Towards the top, general operating features. There's a table in here that sort of discusses using the mouse, and right mouse, left mouse, and what operations are associated with each. So we'll cover those, but here's a reference you can always get to refer to. Okay, so firstly, let's talk about how do we make things bigger or smaller. Okay, so zooming in or out. That's with the center mouse wheel. That's the easiest way to do that. If for whatever reason you have just a right and left mouse and no center mouse wheel, I believe you hold the shift key down and the right mouse button will also affect this zoom in and out. Okay, the left mouse button depressed is a rotate, and the right mouse button depressed is a translate, so either left, right, or up, down. Okay, we covered zoom, which is the center mouse wheel. And then there's one more rotation, which is rotation within the screen plane. So basically, if you hold the shift key down with the left mouse, if you move that up and down, you can rotate the molecule within the plane of your screen. Okay. Okay, now let's take a look at the different model styles available. The default is typically a ball and spoke, which is what we have displayed on screen. These are available under the model menu. This will be a little bit repetitive, but just bear with me. So from the sort of the leanest would be wire or line. Let me zoom in so you can see that. To ball and spoke, to tube. I commonly render things in a tube style. And then we were just looking at the ball and spoke. That was sort of what we had open to begin with. And then finally, let's take a look at the space filling model, or the CPK, either way. This is essentially you lose contact of where the bonds are, and all of the atoms are represented as spheres, and you imply bonding based on the level of interpenetration of the spheres, and also the atoms should be to scale, so the different centers are to scale. So the protons here are roughly to scale to carbon compared to some of the other models where things are not the same. The scale's off. Okay, in any event, so this is the most physically realistic, I would say. So this covers the different model styles. There are a couple of others, line and hide. Those will be discussed in further tutorials. Okay. Okay, let's click in the lower left step key to advance to the next molecule in the list. And the next molecule is actually a dimer. It's an acetic acid dimer. And we have a nice opportunity to display hydrogen bonding here in two locations. So go to the model menu in the upper left. And if you'll turn on display of hydrogen bonds towards the bottom. So there's an atom and an angle and a distance criterion, but essentially if the system meets the criteria, Spartan will display a hydrogen bond. And this can be also essentially calculated and displayed using the electrostatic potential map. You can vary the ISO value or the electron density value to highlight hydrogen bonding as well. But anyway, this is just a model style under the model menu. Okay, let's use the step keys again in the lower left to move to the next model, the next molecule rather, which is propene. And here we will use the geometry menu. So also towards the upper left of the menus is the geometry menu, and let's do the measure distance, the first entry. The geometry menu has access to a whole host of items, but let's look at measure distance, angle, and dihedral shortly. Okay, measuring distance in propene, you can just pick any bond length or any two atoms to measure. So let's look at this bond distance here, 1.5 angstroms. The same data could be obtained simply by clicking on the bond, also 1.5 angstroms. And you'll note that with either the distance between the two atoms or the bond length displayed in the lower right corner of the interface, there's also a little downward arrow, a little yellow arrow. And if you click on that, that simply posts that distance into the spreadsheet, whatever's been measured. Okay, so we're not confined to bonds. I mean, if we want to measure the distance from, for example, from this proton on the methyl group over here to this proton over here, you can do so. And again, you can always post with this value. And the same is true whether we're measuring distance, angle, or dihedral. You can post into the spreadsheet. Okay, using the step keys now to move to the next model in the list, ammonia. let's go ahead and grab from the geometry menu a measure angle tool, and let's measure the hydrogen, nitrogen, hydrogen bond angle, and we find that is 106.3 or something like that. Or you could simply click on two of the two bonds. Two bonds would define the angle as well. Okay, and then let's move to the next molecule in the list, and that is hydrogen peroxide. And this one will just simply measure from the geometry menu, measure dihedral angle. And so we'll just go from hydrogen to oxygen to oxygen to hydrogen. So the only dihedral available. So either clicking on 4 atoms or clicking on the 3 bonds that form the torsion or dihedral angle. And you see that's posted in the bottom of the interface, and you can post that into the interface as well. Not the interface. You can post that into the spreadsheet. Okay. So the next molecule on the list, acetic acid. Okay, we will use acetic acid, not acetic acid dimer, but acetic acid to demonstrate the properties dialog. And what we'll do is we'll open that, and you can do that in one of 3 ways. Let me demonstrate those. It's this sort of blue bubble with the I inside of it. I for information. Okay, that icon is typically a permanently displayed icon in the toolbar. It's also available under the display menu. So display menu properties. And then a third way is if you just right click on the background in Spartan, the bottom entry is properties. So irrespective of how you get there, open the properties dialog. And I just make a couple of comments. Firstly, I have increased the font size in my interface to kind of a gross size, which makes the dialog not look too nice, but hopefully it makes everything visible. The intent is to be able to see things once this is uploaded, so hopefully you'll be able to see everything. I think I'm at font 14, and typical is maybe 10, so it looks tighter and a little bit cleaner. In any event, the other comment to make is the properties dialog is modal, and it depends on what has focus. With no items with focus, without any selection on my part, the molecule properties dialog is displayed. So we'll look at the molecule properties dialog. We'll also take a look at an atom properties dialog as well. So what's included? So it's a multi-tab dialog. There's a molecule tab. There's a QSAR or structure activity tab, thermodynamics tab, all property data. And every time you see these post buttons, these yellow arrows, this means you can post the data into the spreadsheet. There's a heat of formation tab, an NMR tab, an estimates tab. This uses the new neural network models. And then there's a utilities tab. Okay, so let's quickly talk through these. The molecule tab includes, a goodly amount of information. We've got the formula, the name, the energy of the highest occupied and lowest unoccupied molecular orbitals, the number of conformers, which in this case is 1, the weight. It's got the calculated energy from whatever theory level was used to run the calculation, and a dipole moment. I may have missed some items. But those are all available, and as far as the dipole moment is concerned, you can turn that on and off as a display. Sometimes that's better done with a different model style. Okay, so the QSAR, a bunch of QSAR properties. So area and polar surface area, volume, ovality, things like that. There's an alternative to polar surface area called polar area that comes from the electrostatic potential map that's available, and you can grab that, the accessible or the standards data size, and you can vary the electrostatic potential range as well. So it's an alternative to polar surface area that's available. Max and min values for calculated surfaces, log P polarizability, and then hydrogen bond donor and acceptor counts for every molecule. Okay, thermodynamics. If an IR calculation has been submitted and completed, that will be available. And included under thermodynamics is entropy, enthalpy, Gibbs energy, 0-point energy, and heat capacity, as well as the ability to change the temperature. And if a specific scale has been applied for, I think, 3 or 4 models, there's a scaling factor applied that will be displayed in the thermodynamics tab as well. Okay, the heat of formation tab will display just that from the experimental heat of formation. That's coming from the NIST website, if it's available. In this case, it is. Also, from the Spartan Spectrum Properties database, we get a T1 heat of formation from the T1 model, and then a DFT heat of formation calculated as well. The NMR tab, I'm going to come back to this. We'll do this one last. Estimates is new. It doesn't have a lot of utility in this particular list file, but it will. It basically says, hey, if I have an Omega B97 XD geometry from 631G star, I can project with better models on a bigger basis set, I can project energy. And the other items in here don't matter because this isn't a conformer distribution file. If it were, you can get Boltzmann weights and things of that nature. Okay, and then finally utilities, and then like I said, we'll come back to NMR, but utilities offer a set of standard tools that can be used to reset models, styles, and atom colors, and apply different label rules, and just a number of utility type functions. Okay, those are included under the utilities. Okay, let's just jump back to NMR quickly. Assuming that NMR calculation has completed successfully, this tab should be available as well. Some of this data may or may not be available. This is a comparison with experiment, and experiment in this case I believe is coming from the NMR shift database. I'm not 100% certain, but I think so. So in the case of acetic acid, not terribly interesting, but if we had a novel compound, some natural product or something like that with a number of different stereo centers, we could run the NMR calculations on a properly Boltzmann weighted set of stereoisomers and be able to, say with pretty good assurance which one is the appropriate assignment as far as stereochemistry is concerned. Anyway, so this is at the molecular level, the NMR data, but this is a good segue also into the atom properties. So you can get to the atom properties simply by clicking on an atom. So I just clicked on this methyl carbon, and we'll get its name, its symbol, and then a set of charges. There are 3 charge models: the electrostatic charge, Mulliken, and natural, and then also a calculated chemical shift if we've run an NMR, which we have in this case, which I guess is, what does that say, 18.8, and then the experimental shift, in this case it's 20.0, so it's very close in this case. What do we have the other one? That's reasonably close too. In any event, so atom properties are available as well. Okay, so now let's go ahead and move to the next. We won't go into properties of other items. Let's move to the next molecule in the list, and we do that with the step keys. This is water, and we're going to look at infrared. Okay, we will use water and the next molecule, cyclohexanone, to demonstrate the IR spectra plotting. And you can get to all of the spectra plots in Spartan from the display menu spectra, or it's the little IR sort of looking spectra icon that's up to the right hand side, just to the right of the electrostatic potential map icon. Okay. Clicking on that will expose a pane. Here I'll zoom in a little bit on the molecule so we can still see things. And in the upper left corner of the pane or panel, you'll see a little green plus icon which says add if you hover over it. So click on that, and let's add the calculated IR. for water. And this looks pretty familiar. We got sort of 3 peaks. We know about the 3 vibrational modes. You can probe this by sort of, if you left mouse and then depress over the plot, you can hover a little probe and it will highlight when you get to a vibrational mode. It's a little touchy though, so I actually find it better to access that from what's called the table. Just immediately under the plus icon, there's a little table icon, and if you click on that, the vibrational modes, and I apologize, this is hard to see probably on video, but there's a little table of vibrational, of the frequencies and the intensities for the vibrational analysis. So you can check a little checkbox to highlight a mode, which is maybe a little bit easier than grabbing it from the actual plot. Okay, so the asymmetric and symmetric stretching and the HOH bin. Okay, so this is for water, and then let's go to cyclohexanone. Let me zoom out. Oh, sorry, go back. I should go back to the plots, and let me add both. Let me add experiment. Let me add calculated. Let me add both in this case. So I check both the experiment and the calculated IR in this case. And the experimental data is just coming from the NIST website, and you can see a pretty good overlap between the two. Actually, let me see if I'll make this a little bit larger, even though it'll shrink the size of the molecule. You can see it's a pretty decent amount of overlap, and actually if you turn the tables on, you can see a comparison. These don't line up side by side, but they do line up pretty well as far as the experiment and comparison goes. You can certainly isolate, the kind of the classic carbonyl stretch over here, and that's very close to agreeing with experiment. Okay, let me make this smaller again. Whatever size it's supposed to be. Okay. Okay, so cyclohexanone in here. Let me actually turn that vibrational mode off, otherwise it'll make us go crazy. Okay, so we'll close this, and then now let's go. Let's move to the next molecule. And let's take a look at camphor, and we'll take a look at NMR. Okay, we will use the next 2 molecules to demonstrate calculated NMR shifts in the spectra pane, and we'll do both 13C and proton, and then we'll also look at UV-Vis spectra. Okay, to get to the spectra pane, again, you can do that either from the display menu spectra, or it's the little spectra icon that's typically to the left of the spreadsheet icon. So let's go there, click on the plus icon to add, and then we'll add, let's go to the NMR tab, let's add a calculated 13C spectra. Okay, so here we see the peaks, basically they have the same intensities. Here we see the shifts. You can either click on individual peaks in the plot, or probably easier, you can just actually click on the actual carbons, and may make it a little bit easier if I simplify this by getting rid of the hydrogens just for display purposes. Okay, so there are a couple of ways to work around this, and then I guess the other comment to make is if you want to know how the 13C spectra performs against experiment, we could go to add, and then let's put the experimental shifts here, and this looks pretty good. I'm going to use the center mouse wheel to zoom in. I don't think you can really tell that much when you're highlighting sort of two sort of 2D plots. There's not a lot of, these 2 match each other. It doesn't look like there's a lot of gap between them. But let's go ahead and look at the actual properties dialog. So we'll keep the spectra pane displayed on screen, but let's also open the properties dialog. You can either grab it from the toolbar or from the display menu, or right click on the background, properties. And let's go to the properties of NMR, so the molecule properties in the NMR tab. And here what we can see is, hey, the RMS of essentially the molecule, the carbon shifts for the molecule is 0.94. So within 1 ppm of the experiment. And it looks like there's one, the worst one is about a little less than 2.5 ppm off. So that's not great, but the rest are actually quite good. This is pretty good. So it may be easier to get at the the data from a dialog rather than looking at the spectral plot. And then let me just also point out, if we this is the molecule properties dialog. If I click on view mode and then touch on an atom, I can also directly compare. The calculated shift is just called chem shift 46.2, and the experimental shift is 46.4. Okay, you can click around and see the quality of performance. Okay, similar is true with regard to behavior with the NMR shifts or the NMR spectra for proton. So let me delete this. Let me turn on display of hydrogens. And let's add not the top entry, but one down, which is essentially proton shifts, but with no couplings. Basically, there'll be no splitting. This is just a little easier to look at. And similar to the previous example, either by clicking on an actual peak or by touching on an actual proton, you can highlight the chemical shift, and you'll highlight the peak on the plot. Okay, so these behave similarly. And also, as I think I mentioned before, if you zoom in to get a better view, you can use the center mouse wheel to do that. There's this little indicator that you've gone off scale, the magnifying glass. So if you ever want to get back to the default scale, just click on that. Okay, so a couple of examples from the NMR tab. Let's now move. Let me go ahead and delete these. Let's now move to the next molecule in the list. This is 3-benzoyl aniline and aniline, and that's finally getting to a little bit larger molecule, and we're going to look at the UV-Vis spectra in this case. So move the molecule a little bit to the top area and click on the spectra icon. That way I can get back at the pane. We'll go in and add, under the UV-Vis tab, the calculated UV-Vis. Okay, and this is, move it a little over to the right so we can sort of see the whole range. Okay, so this is a little bit difficult to see. Maybe I'll make it a little bit larger. We go ahead and add also the experimental data, and this is coming from the NMR. Sorry, not NMR. This is coming from the NIST UV-Vis database. There's a small collection of a couple thousand. This is not great. It looks like maybe a similar lambda max. I don't know what this is. Maybe 230, 240, something like that, somewhere around there. In any event, this is probably one of the better looking plots with regard to performance. The quality of the QM UV-Vis shifts is definitely sufficient to let you know if you're going to shift right or shift left or shift red or shift blue if you make a substitution, but it's probably not good enough to assign color. At least that has been my experience. I don't think this was run in solvent either. This is probably just a straight gas phase calculation. Okay, so next let's move to a set of molecules where we will begin to explore graphical data. Oh, now we're back to small molecules. Okay, ethylene. Okay, we will use ethylene in the next couple of molecules or so to demonstrate the graphical surfaces available in Spartan. These are typically accessed via the display menu surfaces. And the surfaces icon looks like the electrostatic potential map. It's actually the electrostatic potential map for the molecule benzene. But before we go there, we're going to go to the orbital energy diagram. And you can always request molecular orbitals from the surfaces dialog, but the orbital energy diagram is sort of a special case tool that we have. So let's click on that either from the display menu, or it's to the left of the electrostatic potential map, to the right of the properties icon in the toolbar. And what that will do is give you a diagram. Typically, we have a small molecule here, so not too many occupied orbitals, but typically it's the top 10 occupied and the top 10 unoccupied orbitals. So you can click on any of these. The scale is in electron volts, so if we click on the highest occupied molecular orbital, that's at -9 or 9.5 EVs. I have mine set in a mesh style so we can see through it, and we could just sort of zoom in. These are calculated on the fly because we have the wave function for the molecule. So I've already run a quantum chemical calculation on this system. But the orbital energy diagram is available. And then if you click on the LUMO, the lowest unoccupied orbital, or the LUMO +1, etc., the energies of these are included in the plot, but they're also down here in the lower right corner. You can post those into the spreadsheet, and there's a diagram in the output that displays these as well. Okay, so orbitals are probably best achieved with the orbital energy diagram, at least for the frontier orbitals. I would recommend going here. If you want to look at something beyond the range of +10, -10, you can do that from the surfaces dialog, and I'll show you that now. So I'll go to view mode, and then I'll go to display surfaces, and we can do that again from the display menu surfaces or the surfaces icon. And just to demonstrate the orbitals, this is accessed via the button called More Surfaces towards the bottom, and then what you do for your surface is you choose the surface of highest occupied minus or lowest occupied plus, and then you can go in and say, hey, I want my highest occupied orbital -5 or whatever, and say enter. Okay, and let me also put that in a mesh mode. Okay, so those are all available from the surfaces dialog. And let's go forward now and talk about things beyond just molecular orbitals. Let's go to the next molecule in the list, which is, I believe, benzene. And we'll pick up with the electrostatic potential map. Okay, let's go ahead and use benzene as the sample molecule to demonstrate the electrostatic potential map. The way to request this is from the display menu and the surfaces dialog. The surfaces dialog is also a permanently displayed icon, and it looks actually like the electrostatic potential map for the molecule benzene. So no matter where you access it, go ahead and open the surfaces dialog. Mine will look a little bit different than yours. Let me move benzene off to the right and sort of describe this. Just quickly, the electrostatic potential map is a composite map. So it basically has taken a separate graphical model and map that on top of the electron density. So let me demonstrate that quickly just to define what the map actually is. Okay, so the electron density is answering the question basically, where's a 99% enclosure, or where's the probability of encountering most of the electrons? Or another way of thinking about it is, how big is this molecule here? Let me turn on the space filling model so we can sort of see the CPK data. It basically overlaps with the electron density. So the electron density essentially answers the question, and I'll do it a little bit more mathematically. Let me put it back in balance, but it answers the question, where is the density 0.002 electrons per cubic atomic unit? Or maybe a little more earthy, if you click on the properties dialog and then actually click on the map, click on the surface rather, that will display the surface properties. And you can see this says, hey, I'm at a ISO value or a density of 99%. This is sort of 99% enclosure. And you have the option to play some games here. But essentially at 99% enclosure, this will highlight the area. How close can I get? And then the question of composite maps, there are a few different options. We can use the electrostatic potential, and that will sort of answer the question as far as charge is concerned. How do I feel? So we sort of can make a charge map with the electrostatic potential, which I'll show in just a second. There's also the local ionization potential map, which can answer the question, if I'm after electrons, how easy is it to take electrons? How relatively easy or difficult is it to remove electrons from a location? And then there's another map that we use that's the absolute value of the LUMO mapped, the lowest unoccupied molecular orbital mapped on top of the electron density. that can often be an indicator of nucleophilic chemistry, or where nucleophiles would be interested. So these are all defined and elaborated in the activities menu. Let me just show you that. Activities menu, if you go to the topic section, which is the second entry, this will just open a little HTML dialog, but let me make it a little bit larger and zoom in. So down towards the bottom, there's atomic orbitals, electron densities, electrostatic potential maps, and then some additional local ionization and LUMO maps are described here. So these are individual PDF files. So get some additional information here, but just to demonstrate where these things are located. Okay, so with regard back to benzene with the electron density displayed. So this is essentially how close one can get to benzene. And then one might ask the question, if I'm probing the charge, if I'm a point positive charge at infinity and as I approach benzene, how do I feel? So as I approach the protons, I'm repelled, and as I approach the pi system, the electrons above and below the ring, I'm attracted. So let's take a look at that. And that's what this surface is, basically saying I feel a level of attraction, 80 kilojoules, above and below the ring. But the electrostatic potential map goes a little bit further and says, hey, at every point on the electron density surface, tell me how you feel. Tell me what the potential is. And in fact, give me a color based on that. So let's go ahead and turn that on. For benzene, that looks a lot like this. And by default, we display this in a banded rendering, sort of discrete bands. But what we can do is go to the properties dialog again, and then if you click on the map, if you click on the surface, you'll get the surface properties, and you can turn bands on or off. If you turn it off just for a second, it's actually quite pretty. But essentially this is defining how close can one get to benzene, and where, if I was an electrophile, where would I be interested is the area defined in red, and where would I be sort of pushed back or repelled is the area defined in blue. Okay? And let's go ahead and take this concept a little bit further. Let's use the same idea. We're going to look at density. But we're going to look at the concept of ionization potential. And we'll do that with the next molecule, which is aniline. Okay, let's use aniline to answer a somewhat related but slightly different question. Instead of asking the question from a charge perspective, as we do with the electrostatic potential map, we'll look at a surface that's called the local ionization potential. So ionization potential is essentially asking the question, how easy is it to remove electrons relative to other locations? So we'll go to the surfaces dialog again, and I'll hit there from the toolbar from the icon. And again, mine looks a little bit different than yours. I think just the local ionization potential is highlighted for you. I want to focus on just two other things quickly. Let's ask the question from a charge perspective. Where is the negative charge? If I was a point positive charge and approaching this, where would I be interested if I was an electrophile in chemistry? So above and below the ring, and also over the amine. Okay, so also over the nitrogen. Okay, but let me turn this off and look at this from a electrostatic potential map perspective, and we'll basically highlight the same areas. So above the ring and over the amine. Note, of course, on the opposite side, there's also attraction, but there's a little bit of repulsive forces coming in from these two protons here, these two hydrogens on the amine. Actually, specifically directing, we'll see ortho and para. We'll see a little bit of that. I think it looks like that's where we highlight. Okay, let's go to the local ionization potential map. We'll turn that on. This is cute. It looks like a little smiley face. Okay, so we highlight the area over the amine, over the nitrogen, and then also the pi ring, but specifically we highlight ortho and then para from the amino group. All right, from the amine. And then on the opposite side, of course, it's only those groups that are highlighted. Okay, so this gives a little bit of an indication of using the electrostatic potential map and the local ionization potential map as a regio selectivity indicator. And what we'll do in the next tutorial is talk about an indicator of nucleophilicity. At least with regard to small molecules, what one can do is take a look at the unoccupied orbitals and map those on top of the electron density. We'll do that with the next molecule, which is cyclohexenone. And we'll take a look at that next. Okay, let's use cyclohexenone as an example for looking at what we call the LUMO map. It's actually the absolute value of the lowest unoccupied molecular orbital, and that's mapped onto the electron density. This is often used as an indicator of nucleophilic chemistry. So as organic chemists, we kind of know that I might be able to do sort of a carbonyl addition up here, or maybe a conjugate addition or a Michael addition down here. But let's use graphical models to sort of identify how that's possible or why that's the case. So we'll go back to the surfaces dialog. So either from the display menu surfaces or from the surfaces icon. And let's firstly turn on, make this a little bit larger, move it to the side. Let's firstly turn on the LUMO, the lowest unoccupied molecular orbital. And we see that it's over the oxygen, but it's also certainly over the carbonyl carbon here, and then also the beta carbon. So this sort of highlights the locations where we know chemistry happens. But let's look at this as a map and sort of take a closer look. And what this is the absolute value of the LUMO mapped onto the electron density. Make it a little smaller. And this highlights the two spots. I mean, you couldn't do a better job. But this certainly highlights the locations for carbonyl and Michael addition. But let's go a little bit further. It's not always to say that it's the lowest unoccupied molecular orbital that's involved with the reaction, and you can certainly map other orbitals onto the density surface. And furthermore, with customization, let me turn on the properties dialog and just remind you, if you click on the surface or you click on a bond or the molecule or whatever you have selected, you have the option to hit the properties dialog. In this case, to better highlight things, if I wanted to, maybe make 5 bands exposed, for example, to better highlight, or to change the range. You've got customization to do that. So there's a lot of flexibility with regard to the display of surfaces as well. It's a little bit more than just what you get when you turn the surface on. Okay, now let's look at the remaining 2 items in, or at least I guess it's really 1 item. The remaining 2 molecules in the list file, which fall under the NMR heading. So the next thing I'd like to do is, well, I guess we'll wrap up with a number of items. Firstly, this is a natural product, camilexin, an alkaloid. I just want to point out I've now labeled specific atoms with the calculated chemical shift. So each one of these carbons, 1, 2, 3, and 4, have been labeled individually. They've been turned on. Okay, so how did I do that? Firstly, how do I turn labels on in the first place? Let me point to where that is again. As a reminder, that is under the model menu and labels. Okay, in this case, labels have been configured to display the calculated chemical shift. Let me show you where that's located. That's under the model menu, configure. And we can configure labels in a host of here, let me go to just to label, for example, to label things by their atom number, their atom label in the file. You can configure labels in a host of manner, but let's say that we're at the calculated chemical shift. So this is coming from DFT calculations in Spartan. Okay? And then let me go back to the model menu and just turn labels off. So why are these 4 individual labels on? And I'll just give you a quick answer. This is a little customization that we didn't look at, but we have previously seen the properties dialog, and we've looked at the atom properties dialog before. So let me go to the properties dialog. I'll move that over here to the right. And I'm just going to click on this particular atom, carbon 5. And you can see that the chemical shift up here, 140.7, this is the calculated shift, is what's displayed. And there's additional information about the charges, and we've seen this before. At the very bottom right of the atom properties dialog, there's a little toggle, and this will take you to an auxiliary menu where you can actually turn on either permanently show or permanently hide, or leave in an ambient mode the label definition. So ambient means just follow what the menu says. If labels are on, turn labels on. If they're off, turn labels off. Show means permanently show no matter what, and hide means permanently hide. So what I've done is I've permanently shown the labels just for these 4 atoms. And the main reason I did that, and I'll move this again a little bit over here to the left, is to compare the results of a density functional calculation, and I'll just show you equilibrium geometry and NMR done with density functional, and this also uses a GIAO approach to calculating the NMR shifts. Okay, so these are the results from density functional, and then in the next file what we can look at are the results from essentially a similar calculation. We'll do energy with DFT, but the underlying equilibrium geometry is coming from an estimated density functional model, and that's using a neural network. And this is new to Spartan 24. And then what I'll do finally is, let me pull up the spreadsheet to just turn display of both the previous file, previous molecule, and this current molecule on at the same time, just so we can get a feel for how well the models behave. So you can see, I mean, this is actually a pretty good example, but within a few ppm, the neural network geometries can reproduce chemical shifts. And this just means that they can reproduce the density functional chemical shifts. This is not a comment on how well the density functional chemical shifts perform against experiment, although those do quite well also. So at this point, we'll leave you at the end of the walking through Spartan tutorial, and we will pick up next with how to build in both 2D and 3D.